When we talk about the solar system and all the planets and all the distance between them, it is very easy to forget that most of the solar system is actually Jupiter and its dozens of moons. So today we continue our look at colonizing the solar system by focusing on Jupiter. I've pointed out in the past that the asteroid belt is in some ways a far better prospect for colonization than the inner planets, and that we focus too much on those inner planets, and something similar applies to Jupiter. Virtually all the mass of the solar system is in our Sun. Of what remains, the majority of it is in Jupiter. If you totaled up every bit of matter in between Mercury and the Kuiper belt, every planet and moon and asteroid, you still would not match the mass of Jupiter. Yet at the same time, that mass is mostly useless to us because Jupiter is not a place we can directly colonize. We are going to challenge that today, near the end of this episode, and discuss ways to colonize the actual planet. But first, we need to consider that Jupiter is not alone. It has a swarm of planetoids, 4 of which, the Galilean moons Ganymede, Callisto, Io, and Europa, are of a size and mass similar to our own moon or the planets Mercury and Pluto. The 8 official planets are also the 8 most massive objects in the solar system, after the Sun of course, but of the next 6, 4 of them are those 4 Galilean moons, and the other 2 are our moon, which we've devoted multiple episodes to discussing the colonization of, and Titan, which was our last episode in this series. So the importance of these 4 moons in colonization should not be underestimated. They are essentially planets in their own right, orbiting a gas giant that's closer in mass to being a star than a rocky planet. In a way, they are not so much a part of our solar system as a miniature one are their own, and if you settled them, the light lag for communication would be seconds, not minutes or hours like talking between other planets. Travel times are on an order of hours or days, depending on your drive system, rather than months or even years for interplanetary travel, and fuel consumption is far lower. At last count, Jupiter has 69 moons, and every single one of them is colonizable. It also has 100 times as many Trojan objects and a planetary ring. We are interested in every single one of these objects, and, out of them alone, you could build a planetary empire that dwarfs most of the interstellar ones we see in science fiction. Now, in Interplanetary Trade and in previous episodes of the series, we talked about how each of our prior colonies needed something the others had, and lots of it. But we also talked about how the Earth was a bit of an exception since there really would only be a demand for precious metals, and Earth doesn't really need them anyways. They just wouldn't mind having them, and importing those can fund solar expansion. The same is also true for Jupiter, since this world and its moons contain all of the raw ingredients necessary to support life. And, as we discussed in the Interplanetary Trade episode, you can ship stuff around that mini solar system quite cheaply. Indeed, gas giants and their coterie of moons are better targets for forced colonization than Earth-like planets at the interstellar level, and we discussed why in the Life in a Space Colony series episode, Early Interstellar Colonies. They've got rocks and ice and plenty of oxygen and nitrogen and everything else we need. They also have a ton of hydrogen, which is important if you have a fusion economy, which we tend to assume you do if you are an interstellar civilization. And of course, we already established we had that technology in this series anyways. However, it is worth noting that Jupiter, at 5.2 AU from the Sun, is still close enough for solar power to be a marginal option. Out on those moons, it's much dimmer than a typical day on the Earth, and it is more akin to a cloudy day or a brightly lit house, not a shadowy twilight place. Ignoring temperature and the lack of air, plants can grow at the light levels out at Jupiter, though you'd want to boost them with some supplementary red LED lighting to optimize their growth. Of course, they can't grow on the surface of some of those moons, not just because they are cold and airless, but also because they are bathed in radiation, a serious health hazard to any form of life. Now, we have followed our traveler from the moon to Mars and back to the moon, then to Venus and back once more to the moon, or rather to Borman Station around the moon, then back down to Earth and back to Borman Station and off to Saturn's moon Titan. However, our traveler doesn't remember that last bit. As you might recall, the traveler had cancer and opted to upload their mind to the huge data repositories built on Titan. As we've also discussed in recent episodes though, uploading your mind is not cut and paste, it's copy and paste. So the traveler copied their mind to a digital format and then found themselves still sitting there with cancer. Fortunately, someone finally cured it, so our traveler is alive and well and once more taken up with Wanderjahr and at Borman Station around the moon, still the hub of interplanetary travel. This radiation issue on Jupiter obviously is especially of concern to our traveler. Jupiter's magnetosphere is enormous, 20,000 times as strong as Earth's, and it bathes the inner moons in potent radiation in roving radiation belts that orbit Jupiter. Now, Jupiter actually has 4 small moons closer to it than the Galilean moons, who are 5 through 8, and only the last of these, Callisto, is outside that intense radiation zone. We often hear about Ganymede, the largest moon in the entire solar system, or Europa and its enormous subsurface ocean hidden under the ice, or even of Io, with its hundreds of active volcanoes spewing matter right into the Jovian orbit, which is largely responsible for the specific shape and nature of Jupiter's magnetosphere. But Callisto gets skipped a lot, which is strange since it's bigger than our own moon, coming in third in the solar system after Ganymede and Titan, and is outside the worst of the radiation, making it the best prospect for forced colonization of Jupiter. And indeed, that is where our traveler will be going, to a new colony recently established on Callisto, far enough from Jupiter to mitigate its gravity well and be safe from radiation. Callisto is a natural choice for the first major base in the Jovian system. And while Europa's oceans interest us more, Callisto itself is believed to have subsurface oceans too. Callisto's oceans are possibly more likely to harbor life than Europa's are, as I will explain later. We don't tend to think too much about Callisto as it is cursed by silver metals. It tends to come in second or third on almost any factor of interest to humans, so it isn't as well known as other planets and moons. But it has so many areas in which it is almost the best that it is actually one of the best prospects for colonization in our solar system. Now, we are a little less concerned about radiation here in the late 22nd century, our traveler's miraculous cure from cancer being the very technology that eases that concern. But we can still hardly go jaunty around radiation-soaked hellish landscapes without a care in the world. So we will settle Callisto first, and because it is the late 22nd century, we will do it in style. There is far more space-based infrastructure than there used to be, and we have more technology and more practice with alien planets and moons. When we get to Callisto, we find they've already set up their own mass driver, no orbital stations in the traditional sense. It's almost a big launch loop ramp with a terminus runway, just sitting on pylons high up over the moon, not orbiting it. We match vectors with that, connect and roll on down to the surface, decelerating as we go, like a big highway exit ramp. Down at the surface are dozens of domes with plants inside. We exit the craft and gaze around. The sun is 5 times further away than on Earth, so it is much dimmer, appearing only 5% as bright. But the red-brown light of Jupiter gives the surface a warm glow. Callisto is tidally locked, so Jupiter itself always dominates the sky on one half of the moon and appears 50 times bigger by area than the moon appears from Earth, allowing us to easily identify the constantly changing features on it, like the Great Red Spot, without even needing a telescope. We smile, pleased we came. This is very different from anything we've seen in the inner system. The lighting isn't just sunlight, there's a red-purple glow of supplemental lighting in the domes. First, because it is far from the sun, and second, because even being about 4 times further from Jupiter than our moon is from Earth, it is still tidally locked to Jupiter, This means that it orbits every 17 days, and that's how long its day-night cycle lasts. Most, but not all plants can handle constant light, but a week of darkness is another story, so being able to provide some lighting in that period is important. The other moons have this same problem, only Io, the closest of the Galilean moons, has a near-Earth-length day at about 42 hours. Europa comes in at 85 hours, and Ganymede at 1 week. Though the other 4 smaller inner moons are really no better, having an effective day length of 7 to 16 hours each. This is okay though, because all the radiation they get encourages us to live under rock and ice for protection anyway, so all your lighting is artificial. On Callisto, we can employ the same techniques as on our own moon, thick glass domes with good insulation, and a nice point defense system for dealing with meteors. That's important on Callisto, which is usually considered to have the oldest and most heavily cratered surface in the solar system. But Callisto doesn't need a fusion economy to run it. It does get enough light for solar to be viable, and fission reactors are certainly possible. Indeed, there's probably good quantities of uranium and thorium in the smaller moons, which might be fairly easy to find and extract. There's also plenty down in Jupiter, though that's harder to extract obviously, but it does mean Jupiter gives off a lot of geothermal energy, or jovithermal I suppose, vastly more than Earth and indeed more than Earth's entire solar energy budget. Hypothetically, you could tap that via Seebeck generators hung in Jupiter's atmosphere for instance, and Jupiter is a massive dynamo, so one could also hypothetically tap its rotation directly for electricity. We are assuming fusion as a power source, but it's nice to know there are other options available, and even if solar is a bit weak out here, we can still play the trick of having cheap parabolic mirrors focusing light on solar panels or beaming energy in from closer to the sun. One way or another, Jupiter's colonization won't be hampered by energy concerns. We do still have heat concerns though. Even volcanic Io is much colder than Antarctica, and much like as we discussed with Titan, you have to worry about the places you build melting into the moon. Callisto's surface is a mix of ice and rock. It's like building in permafrost tundra. You don't necessarily want to go warming that up. However, if you are bound and determined to genuinely terraform the place, you can make large thin mirrors to bounce enough sunlight there, and then dome the place over, para-terraform it, so you can create an atmosphere. Of course, gravity is a concern too, since gravity on Callisto is quite low, lower even than our moon at 12% Earth normal. It is more massive than the moon, but less dense. Even Ganymede is only 14.6% Earth normal, and Io is the highest, slightly more than our own moon, at 18%. It's 13% on Europa, incidentally, making Callisto the lowest gravity moon of Jupiter's major moons, and none of the others have any gravity of significance. We mentioned back in episode 1 that we just don't know how much gravity people need. We know Earth gravity is fine, and we know zero gravity is not. Nobody has ever lived in low gravity for more than a few days, so we don't yet know what the long-term effects of being exposed to low gravity are. It could turn out to be the case that Callisto's low 12% is enough, or that Venus's near-Earth 91% is not enough. We just don't know. When discussing Mars's 38% gravity in the first episode, we opted to assume it would be enough with at most some technological and medical assistance. We ignored it on Titan because the folks living there were cyborgs and transhumans. Here I don't think we can. Now, channel regulars know we have a trick for making gravity. We stick folks in a cylinder and spin it around, using centrifugal force to simulate gravity by spin. We can't quite do that here, but we can do something similar. We have to combine the two, real gravity and spin gravity, when working in low gravity environments. We can't just ignore the gravity already present. So if we want to boost it, we need to use something more like a rotating bowl or vase rather than a cylinder. The stronger the local gravity, the shallower the bowl. The weaker, the closer to being a cylinder we need. Now we do have one last trick if you really want an Earth-like planet. Last week in Mega-Earths we discussed building shells around stockpiles of mass, preferably cheap mass like hydrogen, whose surface gravity would then be the same as Earth. For Callisto or either of the other 3 moons, there's enough mass to make a rocky shell surface, and you've got hundreds of Earth's worth of hydrogen just down in Jupiter itself. You could also fix its spin to be 24 hours while pumping that in, and use orbiting shades and mirrors, or ones back at Jupiter's L1 point, to boost the light. And between the 4 main moons there is actually plenty enough rocky mass to construct many such shells, not just 4. But that's a lot of work, and I would say more than it's worth, but we never really know what the effective price point for Earth-like living space will be when considering high-tech post-scarcity civilizations. They might have automation so good that planet building is fairly cheap, or they might be so efficiency-minded that they live a strictly post-biological existence on computer chips. As for Callisto, while its surface resembles our own moon quite a lot, it is a bit different. As you dig down beneath its rocky ice lithosphere, many dozens of kilometers, we think you might hit a deep salty ocean, one which may or may not have a decent amount of ammonia in it too, and which would probably be deeper than any ocean on Earth, before returning to an icy rock mixture and possibly a small silicate core. Unlike Earth, it is a lot easier to dig very deep on Callisto, no major issues with pressure and heat, so boring a tunnel down into that hypothetical ocean might not be too hard. You can do some interesting things there too, but we'll discuss those in regards to Europa in a moment instead. Once settled on Callisto, our traveler finds they are something of a celebrity, having been all over the solar system with every new colony. So we are brought in to discuss the future of the Jovian civilization. For the outer moons, and indeed even those inner 4, things are simple enough. They will follow the colonial model of asteroids by boring a hole inside for a rotating habitat and mine and expand as the situation demands. For Ganymede, the situation is somewhat the same as Callisto, but you almost have to live underground because of the radiation. It is also likely to have an oceanic layer between the surface rock and ice and the center. Io is another story. It tends to get written off as non-viable for colonization, but that might be a little too pessimistic, and as we noted in our discussion last time about Titan, colonization doesn't necessarily mean terraforming. It would not be too hard to put an orbital ring around Io with connected habitats folks lived in, and a tether reaching down to the surface to conduct mining operations. In this regard, Io could serve as an industrial hub, supplying huge amounts of raw materials and manufactured goods to the rest of the Jovian mini-system. Again, with the low gravity and close distances, it is actually viable even with 21st century rocket technology to ship around goods and people between all these moons. But let's consider Europa next. Europa is often considered the best candidate for any other life in our solar system, especially anything more complex than some lichen on Mars or floating microbes on Venus. Data from NASA's Galileo mission strongly indicated that Europa has a liquid ocean under its ice shell that has more water in it than all of Earth's oceans combined, and is more than 100 kilometers deep. Water was one of the main reasons that life evolved on Earth, and many scientists believe it might be a necessary element for the creation of life. There are some issues when it comes to life evolving on Europa though. One is that the most recent resource suggests that an action of having alternating periods in, as Charles Darwin put it, warm little ponds of wet and dry, will likely require to create the conditions for unicellular life to evolve on Earth. For that, there needs to be land where a nutrient-rich soup of chemicals can pool that is alternately covered by ocean water and then dried out. There is no such land on Europa. Another problem is that Jupiter's radiation belts regularly sweep across the surface of Europa, which would sterilize any life on its surface, including any in those warm little ponds. That is, if it is life as we know it from Earth. Finally, the temperature of those ponds is unlikely to be warm, meaning that biochemical reactions slow down and decrease the chance of life evolving from the soup. Now, as mentioned, both Callisto and Ganymede probably have those underground oceans just like Europa, so if you find life on one, you might find it on the others. Indeed, as close as they are, and as low as their gravity is, I would not rule out that if one had it, the others might too, even with those frozen surfaces and radiation belts as a likely barrier to cross-pollination. This means in all three cases we want to be careful to keep our eyes open for signs of life. It is not very likely, but if we find life under the ice on any of these moons, it will shake up our view of the cosmos a lot. If that life exists though, it is likely to be very different from life that evolved on Earth. But even if it was a simple bacterial life form, that would provide a treasure trove of genetic information that we could possibly incorporate into our own genetics or make use of industrially, and that could be an economic driver for the Jovian colonies too. If it is life as we know it, then that will also have repercussions, as it means that panspermia is probably real. Panspermia is the hypothesis that life exists throughout the universe, distributed by meteoroids, asteroids, comets, and planetoids. As I mentioned earlier, Callisto is possibly a better bet for finding life on it than Europa is, because Callisto is located largely outside of Jupiter's radiation belts, has solid rocky surfaces, and therefore may be able to provide us with those alternating wet and dry primordial ponds. The only real issue is that it does not have the tidal stresses that Europa does, so any heating of the oceans will have to be driven by radioactive decay in Callisto's core and by sunlight, not through gravitational tectonics. In the absence of life though, Europa represents an unusual colonization approach. Under the ice is ocean, and in a fusion economy, it would be possible to float large fusion reactors that gave off photosynthetic light to warm the seas and let us transplant photosynthetic organisms and our whole marine ecology there. You could put reactors near the surface and hang a chain of lights down, what I referred to as vertical reefs in our discussion of rogue planets or enhancements to Earth itself. Or you could simply let them float like submarines around the depths with large wire frames around them with lights and nutrients till they became meandering ecosystems fueling an entire marine ecology, submarine archipelagos. With Europa's far weaker gravity diminishing the buildup of pressure with depth, and with light coming from the reactors and not the sun, such marine life would be far more vertical. Human habitats and farms could exist on these submarine archipelagos too, and people might journey around in personal submarines rather than automobiles or small private spaceships. It's hard to overestimate the amount of civilization and colonization that could be done around Jupiter. It has immense resources and a good mixture of them, so that while it might trade with other planets, it doesn't really need to. Yet what about the planet itself? In a fusion economy, hydrogen is immensely valuable, but also not really in short supply. But the preferred fusion methods, beyond simple vanilla hydrogen, which is much harder, would be either deuterium or helium-3, and Jupiter is a great source for both, which are not easy to find in quantity elsewhere. Though one doesn't need a lot for fusion. Entire national economies can run their electricity off the energy in one small tank of deuterium for quite a while. To harvest that, we might scoop it up with ships, giant airships that descended and opened their bays and shot out of the atmosphere before they got too heavy and slowed down. This may be the best method early on, and your ship probably needs to be as big as a fusion reactor can be made small, so that it can be powered by what it is collecting. We obviously don't have fusion reactors for spaceships, but it's unlikely you couldn't make one suitable for that use, and of course if you can't make one at all, you don't need to try scooping up gas from Jupiter. If you do have a fusion economy, then you probably want not just these scoops, but big tanker refineries floating around sucking in gas, and probably refining out the deuterium or helium-3 from it for pickup. However, at the bigger scale, when you need billions of tons, scooping with ships is maybe not ideal. Folks often want to hang tethers down and just suck the material up, either straight from the atmosphere or from our huge flying refineries. But space elevators are a dubious proposition even on Earth, and tethers on Jupiter require far more length and are under 253% of Earth's gravity. We have an option for this though. The orbital rings we've discussed before, the ultimate in cheap mass movement of material off a planet. You build an orbital ring just above the atmosphere, or even down in it just a little to gain protection against meteors but still be above wind. From here you can safely lower down far shorter tethers to scoop up gas and retract them up to the ring. Above that you can have yet another ring, either several layers or two more. One more circular ring out where gravity has dropped to Earth normal, and another elliptical one connecting the two. Jupiter has a radius of just under 70,000 kilometers, more than 10 times Earth's. To get to a place where gravity is the same as Earth, you would need to be 1.59 times further away, 41,000 kilometers above the planet. This is probably much too long to stretch any single space elevator tether, so you need either multiple rings, each connected to the one above and below, or you need an elliptical one to stretch the distance. However, up at the top one you could walk around, under a dome, and feel just like you were back on Earth. Indeed, as we discussed last week, one option for colonizing Jupiter is simply to build mini orbital rings at this distance, each turned at an angle, to create a shell around the planet, then add dirt and water and air, and have a planet with 318 times the living area of Earth. It would be cold, but you can provide artificial lighting either by mini orbital mirrors or an artificial fusion-powered sun orbiting the planet once a day geocentrically. Jupiter is known as the solar system's vacuum cleaner. It is the most massive object in our solar system with the sole exception of the Sun, and it deflects or captures a lot of the comets and asteroids that would otherwise head for the inner solar system. Without Jupiter, considerably more comets and asteroids would bombard the inner planets, including Earth. We can be extremely grateful that we have a big brother keeping watch over us and dealing with those icy and rocky playground bullies that would otherwise pound us. There will come a time, though, when humans have colonized the entire solar system, including the Oort Cloud. The Oort Cloud is currently where most of our comets are found. We will discuss how that can happen in our next episode in the series. When we have tamed it all, rogue bodies will be all but eliminated, and we will outgrow the need for a planetary big brother to protect us here in the solar system. One possible future for Jupiter is to remove all the gas from Jupiter. Down under it all, we believe is an immense core of heavier elements several times more massive than Earth. If we strip that all away, we might have a rather nice planet below, especially if we moved it closer to the Sun and took its moons with it. For this purpose, we have a device known as a fusion candle. There's a few ways to do this, but I'll describe the ones Jeremy rendered for this episode, since they are the only such animations in existence. You build yourself a giant fusion reactor with an intake nozzle to suck in gas and two propellant nozzles, one pointed down and one pointed up. When you turn it on, the upward nozzle hurls huge amounts of high-velocity gas out of a rocket engine, shooting it fast enough to escape the planet's gravity. That would make the fusion candle drop down into the planet very fast, so the second down-pointing nozzle thrusts the whole candle up to compensate. This is one time when you definitely want to burn the candle at both ends. You build a ton of these. When they are on the right side of the planet, they are on full power. Otherwise they hover, so that all your push is in the right direction. And it shoves the planet like a giant spaceship, using its massive atmosphere for power and propellant. By this means, you can strip off a gas giant's atmosphere and relocate the smaller remnant to the inner solar system. That would be a rather pitiful ending for our big brother planet, and I prefer a more exciting option of making the Jovian system into an interstellar spacecraft, taking the whole planet and its moons on an interstellar journey to another solar system. It has the fuel and resources to travel at solid speeds across the interstellar void for millions of years if it needs to, and it is one example of how you might send an intergalactic colonization effort, a notion we will examine more at the end of the year. That interstellar spacecraft Jovian system could even undergo a further evolution. Jupiter is too small to become a star, but that doesn't need to stop us. We can pick up other exo-Jupiters, Jupiter-sized planets that have been expelled from other star systems, or ones that we have flown out of other systems using fusion candles. We gather several of these Jupiters together in interstellar space and fuse them into a super-Jupiter. This superplanet, once it reaches a critical mass, will itself become a star about which we can build a custom-made solar system with our super-Jupiter as its star. Speaking of getting out into deep space though, our next episode in the series will focus on colonizing not planets, but the endless swarm of small icy bodies out beyond the main solar system, in our next episode in the Outward Bound series, Colonizing the Oort Cloud. After that we will turn inward and talk about colonizing the Sun. Not Mercury or making a Dyson swarm, but the actual Sun itself. Next week, though, we will head back to our discussion of artificial intelligence and look at the well-known science fiction concept of a machine rebellion. And the week after that, we will examine the notion of networked intelligence and hive minds. For alerts when those and other episodes come out, make sure to subscribe to the channel. And if you enjoyed this episode, hit the like button and share it with others. Until next time, thanks for watching and have a great week.